with Ankur Moitra, who's going to tell us about hierarchies, SOS, and all that good stuff. So take it away.
Great. Thanks for coming. Thanks for waking up for the morning session. So welcome to part 3 of the Sum of Squares tutorial. So Sum of Squares has a bit of a reputation as being a kind of technical subject, which it is. And some of the algorithms and lower bounds in SOS are actually pretty involved. But what I want to do first is I want to step a little bit outside of my own comfort zone and tell you about how SOS has a lot of implications in other fields. To explain, especially to theorists, how SOS can say interesting things in extremal combinatorics. And then I'll talk about some results in polynomial optimization and tell you how these are really intimately related to quantum, and especially quantum information theory, something called quantum Di Finetti theorems. So I'm hoping that in the first part of this, you're going to get some idea of the reach of Sum of Squares techniques. And then I'm going to conclude with some of the recent lower bounds and the technology in proving lower bounds, especially for planted problems. So they also gave me this directive for the tutorial that I should bore the experts. And this morning I ran into Fan and Ron. So let me tell you, you guys are going to be super bored. You can just go to sleep for the first part. And Pablo, you're going to be bored the entire time. But let's do extremal combinatorics. And I'm going to start off with telling you one of the famous results in extremal combinatorics, which is something which can be proven through Sum of Squares and semi-definite programming techniques. So there's this beautiful picture, which was really completed by Razborov, the last bit of this. So what does this picture look like? So if you take any graph and you look at the triangle density, let's call that T. So that just means I take a graph and I look at a random set of 3 nodes and I measure the fraction of times that I get an induced triangle on that set of nodes. And I also look at the edge density, which we can think about in the same way as sample a random pair of points and how often are they an edge. So you can ask for this particular pair of subgraphs, counting the fraction of triangles and the fraction of edges, what are the allowable pairs of T versus E? So in fact, this picture, what it looks like, now it's completely understood. So obviously you have this corner at 1, 1 where the graph is complete, but you get this curve that looks like T equals E to the 3 halves. And then you get this funny little shape down here that's 0 along the 0 axis until the point half. And then you get something very interesting happening, that along this other dashed line, T is E times 2 to the E minus 1, that you get these funny little bumps all the way up. And this is the truth for this simple question, that if you ask over all graphs what are the allowable pairs of the triangle density and the edge density, this is all there is. So this is a really beautiful picture. And to me, this tells me already that sometimes you see beautiful mathematical works of art out of fractals, but you can also get them out of subgraph densities for proving things like this. So what I want to do is I want to explain a bit about how you can prove relationships between subgraph counts and establish pictures like this using semi-definite programming techniques. Now, of course, this area is pretty challenging, so what I'm going to do is I'm going to prove a really simple result, which is just that, that the picture looks like it does on this line. That in fact, that if you ask for a triangle-free graph, the largest fraction of edges you can have is a half. So this is called Montel's theorem. So let me tell you about this theorem. Let's formally state it. It goes back a long way. So it actually goes back to 1907. And all it says is that if you take a graph G and it's triangle free. So the density of triangles is 0. Then the maximum number of edges you can have is at most the floor of n squared over 4. Where, just to keep the notation simple, we're going to have n as the number of nodes. So this is actually such a simple result that when I was preparing this talk, I realized that we actually asked this as a question on our undergrad discrete math final exam. So this is a really simple question. We do give them a hint about how to go about it via induction. But let me prove this really simple result that you could get through purely elementary undergrad techniques using some really high-powered machinery. But the point is that once you have this high-powered machinery set up, you can get lots of beautiful pictures out of it and understand really the cutting edge of some of these results in extremal combinatorics. So this is going to be our plan for the first part of part 3. Let's prove an asymptotic version of Montel's theorem, that if you have a triangle-free graph, the largest fraction of edges you can have is a half. All right, so in fact, let me tell you, so this is really following a few works. So this is following a flag algebra approach of Falgas, Ravri, and Vaughan from 13. And in particular, I'm going to be following an approach of Raymond, Singh, and Thomas, which took the flag algebra's approach of Razbarov, which he used to establish these types of pictures, and translated it into the language of SOS so that we can understand it in light of some of the tools that Pablo introduced in the first 2 parts of this tutorial. So this is our plan. We want to use sum of squares to establish this simple theorem. So first, let's get started. Let's understand how our subgraph density problem can be translated into polynomials. After all, that's what SOS is about. It's a relaxation for polynomial optimization. So the first key is, well, we can define polynomials that count subgraph densities. So let's see concretely how this works. So let me give you an example. Let's say we take the graph H1. Very simple graph. We have got a graph on 3 nodes with just 1 edge between it. So we can ask, for example, if I sample a random set of 3 nodes, how often do I see H1 as my induced subgraph? So that's a simple probabilistic experiment, but we can also write it in the language of polynomials. So how would we do that? We define a polynomial dH1, which what it does is it looks over all choices of sets of 3 nodes. And what it looks like is it takes xij, which you should think of as the indicator for whether the edge between I and j is present, and it counts all of the different ways that this particular subgraph could occur. So for example, this is one way that the subgraph could occur, and there are going to be 3 other terms. Depending on, so for example, this is the indicator function of these edges being missing. So what this is really counting is when we take the triple ijk, it's asking how often do we have I and j here representing the edge that's present, and then are missing the 2 other edges. Of course, we get 3 other ways to do this. So we get this polynomial. Let me just write it out just to be concrete. And we get the last term is xjk, 1 minus xij. Okay, so this is what I'll mean when I talk about using polynomials to compute subgraph densities. All you do is you take whatever your graph is and you write out a polynomial using this type of framework. This is how we would do it in the case of H1. You can define it formally for, all graphs using injections, but let's not do that. Let's instead relate this back to subgraph count. So the point is that if we take this polynomial dH1 and we evaluate it on the indicator function of some graph G. So what I mean by that is we have n choose 2 variables, 1 for every pair of nodes, things like xij. And all we do is we take our graph G and we plug in a 1 for an xij if that edge is present. We plug in a 0 otherwise. So the easy thing to see is that the way we've done this, when we plug in the indicator function of the graph G, what the polynomial evaluates to is it evaluates to the probability that 3 vertices chosen uniformly at random induce a copy of H1. All right, so now we're starting to be in business. We have a way to translate subgraph densities into polynomials, and the name of the game is to try and prove relationships between these polynomials using the sum of squares framework. But in fact, there's one more crucial ingredient we'll need, which is that this result is only about triangle-free graphs. So somehow we have to figure out how to exploit the properties of the graph, namely that it's triangle-free, when we're proving relationships between subgraph counts. So the way that we're going to do this, I'm going to strip away a lot of the language that's usually used in these papers because it's much simpler in this one case we're looking at. So let me define the following. I'm going to let z of I be the indicator function of all graphs where G is triangle-free. The reason it's written as z of I is because a lot of times you talk about this as the zeros of an ideal. We won't really talk too much about this, but let's just define z of I this way. Now the crucial ingredient is what we're going to do is we need a notion of when polynomials are equivalent. So we will, it's too low for me. All right, so we will say that two polynomials, P and Q, are equivalent mod this ideal if and only if P of x equals Q of x for all x in the zeros of this ideal. So let's translate what this means. This is our notion of when polynomials are equivalent, but it's also the thing that's going to be capturing the triangle freeness of our graph because that's how z of I is defined for our purposes. So let's just understand what this means. So what I claim is that if we let H3 be a triangle, then we can do the same thing where we take this triangle and we write down a polynomial d of H3, which for any graph G, we plug in the indicator function of G, and we plug that into the polynomial, we would get the density of triangles. But what I claim is that now when we're working with this ideal that we're interested in, where we mod out by these triangle-free graphs, then what I claim is that d of H3, this polynomial, is equivalent to the zero polynomial mod I, just using this definition. Because what this means is that when we take any graph that's triangle-free, which we plug into this polynomial, its indicator function of that graph, we're going to get the same thing as we plugged it into the all-zero polynomial. That's just because this left-hand side counts the fraction of triples that have triangles, and there are none of them by assumption because we're starting off with a triangle-free graph. So this is a way to illustrate what this definition means and what working modulo an ideal buys us, is that once we have this ideal in mind of working with a triangle-free graph, we get some nice identities. Like d of H3, which is defined generally for other graphs, well, once we're working with this ideal, it's equivalent to the all-zero polynomial. So let me know if you have any questions, but this will be one of the crucial definitions. So now what I want to do is I want to start using this technology about how to write subgraph densities as polynomials and how to work modulo an ideal to start figuring out some elementary relationships between the different polynomials that will be characters in the story. So how do we do this? So let's define the subgraphs we'll be interested in. So I'm going to start off with, we'll have three subgraphs. We can take H0 as the empty graph on 3 nodes. H1, we've already defined. That's the same thing. H2 is the 3-node graph which has 2 edges. And H3, as we defined it, is the triangle graph. So now for each of these graphs, I can write down this polynomial d of H0, d of H1, and so on. But what I claim is that we get some simple identities out of these things. What I claim is if we define a polynomial d, which counts edges, so it just evaluates to the edge density. So what is this polynomial? all it is it sums over all pairs of nodes, xij. So when we plug in the indicator function of a graph into this polynomial d, all we get out is its edge density. Now what I claim is that we have some nice relationships already that we can reason about. What I claim is that this is the same polynomial as 1/3 of dh1 plus 2/3 dh2 plus 3/3 dh3. So just to make sure we're all on the same page, can anyone tell me why this is true? Why these two polynomials are equal? Yep.
Because you can count the degrees in two ways. One using those subgraphs, one's just...
Perfect. So this is just another way to count the edge density of a graph. Instead of actually doing this experiment on the left-hand side where we choose two random nodes and ask how often there is an edge between them, well, we can instead do an experiment where we count a triple of nodes. And we look at how many induced edges we get in that triple. You know, if it's h1, then we get 1 out of those 3 edges as present. If it's h2, we get 2 out of these 3 nodes. These 3 edges are present. If it's h3, we get 3. And there's no contribution from h0 because it's 0 out of 3 edges. But now what I claim is that this polynomial is equivalent to 1/3 dh1 plus 2/3 dh2 mod this ideal that we care about. So why is that? That's because we already proved that this guy is equal to 0 once we're working with triangle-free graphs. If you do this experiment on the right-hand side where you choose a random triple of nodes and count how many induced edges you have, you never have to worry about the contribution of the triangles because by assumption there are no triangles. So this is already one simple identity. That's just a thought experiment about doing a probabilistic experiment, one on the left and one on the right, in the language of polynomials. So let's prove one more elementary identity before we get to something called flags. So what I claim is the following, that the all-one polynomial is equivalent to dh0 plus dh1 plus dh2 mod the ideal. So this is once again a simple experiment. See, what you have is that the all-one polynomial is equal to the polynomial d of h0, d of h1 plus d of h2 plus d of h3. Because what that's really saying is that if you do an experiment on the right-hand side where you choose a random triple of nodes and ask how often do you get one of these 4 graphs, then you always get exactly one of them. So that's why 1 is equal to that sum. But once you work modulo the ideal, you never have to worry about triangles. So you can just cross off that term once you're working mod I. So does this make sense? Any questions about this? All right. So we've got our technology in hand. We've got our language of how to use polynomials to count subgraph densities. We've got this notion of working modulo an ideal that takes into account the structure of G, that it's triangle free. And we have some elementary identities. We're going to need slightly less elementary identities to prove Montel's theorem, which this is going to take me to this notion of a T-flag. So let me define this last graph theoretic concept. We're going to define it, and then we'll talk about how to count it using an appropriate probabilistic experiment and get some last identities that will be enough to prove Montel's theorem. So let me define the notion of a flag. It's roughly the same thing as what we've been doing before. We're counting subgraph densities, except we're going to do it with some of the nodes being labeled instead. So this definition is a little bit of a mouthful, but it's really crucial. So we're going to talk about a flag, which starts off with a little t vertex graph, capital T, where every vertex has a distinct label from 1 to little t. Okay? Now, the important point is then we can use it to define a capital T flag. It's just a graph which has this graph as its core. So that's what this definition is capturing. So a T flag f of size, little f, is just a graph with little f vertices and T distinct labels from the set T that induces the core. With the labels being correct. All right, so let me say this informally because I warned you this definition is a little bit of a mouthful. You start off with some core graph, capital T. All it is it comes along with labels where every vertex in capital T is labeled with a distinct label. That's the core. And then this flag is just some sort of ornate thing hanging off of it. It has the property that hidden inside F is this induced graph T with the labels being correct. And then there's some other vertices which are not labeled, which they can do whatever they want. So this is the notion of a flag. And the flags that we're going to use are actually really simple flags. So let's just define them up front. The flags we're going to use are F0, which is just the empty graph on two nodes and has one label. So little t is 1, and this node is labeled down here as 1. And F1, the other flag that we'll be interested in, is just this two-node graph with a single edge where this node is labeled. So these are both flags of a really simple graph. The graph you have, this is capital T right here, is just the single node graph that has a label 1. And these are two ways of hanging off unlabeled structures off of them to get the flags F0 and F1 respectively. So what we're going to do is we're going to define a way of counting flags, actually pairs of flags, in a graph. And we're going to use that as our way to create sum of squares proofs about subgraph densities. So the same way that when we defined D of H1 and other things like this, there was really a probabilistic experiment that was sitting underneath it. That I did write out explicitly what D of H1 is, but to do so for more and more complicated graphs becomes a huge mouthful and a large expression. But let me instead explain how to think about counting pairs of flag densities as a probabilistic experiment. So, and you should think about how this translates into a polynomial. So what I claim is we can count pairs of flag densities. Let's call this pair, for example, F and F prime, just for simplicity. So the idea is, see, when we had this probabilistic experiment, we just chose a random subset of 3 nodes and looked for an induced subgraph. What we're going to do here is a little bit different. First thing we're going to do is we're going to fix labels of T random vertices in G. And these labels, as you would expect, are going to have distinct labels from this set, little t. So first thing you do in your probabilistic experiment, yep?
I didn't understand what you mean by counting flag densities in a graph, because the graph doesn't have labels, right?
Right. So I'm adding labels randomly. So ask me the question again when I get to the full probabilistic experiment, but what I mean by counting pairs is this probabilistic experiment, is that we're going to choose only the labels in some set 1 through t. We're going to choose those nodes randomly out of the graph, and then we're going to choose the unlabeled parts. So what's the remaining part of the probabilistic experiment is, remember that our flag has little f minus t other vertices that are unlabeled. In this case, just one other vertex that's unlabeled. So what you do is you choose f minus t and another f minus t, because we're interested in pairs of flags, vertices. From G. And what you look at is you're interested in the probability that they disjointly induce F and F prime. So remember that these pairs of flags, we're going to assume that they come from the same core graph T, the same way that these two flags come from the same core graph, which is just the single node graph with a single label. And what we're going to do is we're going to do this probabilistic experiment where we choose where the core is by choosing a random set of T nodes, labeling them with distinct labels. And then we fix whatever is the remainder in the two flags, F minus T nodes for F, F minus T nodes for F prime. And we ask what the probability is that these two sets of nodes disjointly induce capital F and capital F prime. So what I claim is just to get an idea of, so this is the probabilistic experiment, what I mean by counting pairs of flag densities. But yep.
So when you choose the other F minus T, you choose them uniformly disjoint from T, but are they also disjoint from each other, or you?
That's a great question. So this is, so there's always the subtlety that you can actually choose them without these two sets being disjoint, but you're thinking of little f and little t as being much smaller than the number of nodes in the graph. So there's a very low chance that they overlap. Now these are the error terms that are going to come up in our sum of squares certificate, so I'll say more about that. But this issue is a serious issue. It's just that it really won't matter for our purposes because it'll contribute lower order terms. Yep.
What about the labeling when you fix, how do you, labeling random?
Yep, so you choose T random nodes uniformly at random, and then you choose a labeling with distinct labels uniformly at random for those T nodes. Make sense? Any other questions? All right, so let's try and understand this probabilistic definition the same way by proving some elementary identities about these pairs of flags that we have in mind. That'll be a good way to make sure that we understand what exactly this experiment is doing. So let's do that. So I'm going to call, for example, let's look at D of F0, F0, which is just the density. It's the polynomial that captures this probabilistic experiment when both of our flags are F0 and F0. So let's prove some identities about this. So what I claim is that this is equal to, we can relate it back to our original subgraph counts in terms of the HIs. What I claim is that it's actually the sum of these two polynomials. So if we do this experiment where we choose a random, we follow this recipe, and we count how often we get the pairs of flags F0 and F0, we can relate that to the experiment of choosing 3 random nodes, where when we choose 3 random nodes, we can ask the question, condition, if we get H0, for example, and then we choose the rest of how we've defined the flags, the labelings, right? So once we fix 3 nodes, that's like fixing the core and the things hanging off the core, but not which one is which. Then you're going to choose uniformly at random from these nodes which one to label 1. And that's what you would get out of this probabilistic experiment. Now the point is that whenever you start off with the subgraph H0 as the thing that's induced in your 3 nodes, it doesn't matter now where I place the core. Wherever I place the core, let's say it's here, so I label this guy 1, and this guy becomes F and this guy becomes F prime, that's a case where we've disjointly induced a pair F0 and F0. So anytime we actually find this empty 3-node graph, we're always going to find the pair of flags we're interested in. So that's one part of this identity, is that every time you get H0, you're going to get the pair of flags in this probabilistic experiment. Now the other part's more interesting. What if, for example, we take H1, that's the induced subgraph we find on 3 nodes. Now we still have to choose the remaining randomness in this experiment, where we label which node is the core node and which partition looks like this pair F and F prime in our pair of flags. So this, I claim, if we started off with this graph H1, there's actually only one way to end up with the pair of flags F0 and F0. So can anyone tell me what the only way to do it is?
Isolate the first.
Exactly, right? So the only way to do it is if this guy is labeled 1, which if this guy is labeled 1, it doesn't matter what happens to the other pair of flags, because that edge between them doesn't show up in any one flag. So disjointly, these two sets really do induce the pair of flags F0 and F0. So this is already a very useful identity for our purposes. Let's do the same thing for other pairs of flags and figure out what these identities look like. So this is just a sort of fun combinatorics. So let's look at the pair F0 and F1. This is the same thing as doing F1 and F0, so let's do both together. Now what I claim is that this is 1/3 dH1 plus 1/3 dH2. So this is more interesting. Let's look at H1, for example. So we start off with inducing this subgraph in our triple of nodes. So what do we do? What do we need to do to be able to induce the pair F0 and F1? So what I claim is that there are actually two ways of doing this. See, for example, we could have the label 1 here, and then we could have this being our set F0. Then indeed we get F0 here correctly, and for the other guy we get F1 as we need. So this is one way which we're using the fact that we have a third chance of labeling this guy as a 1, and we have a third chance of this set being F0. Right? Yeah. And so you can do this other ways too. So for example, oops. So for example, I could induce 1 down here and have this guy being the pair, right? This could be my, F0 down here. This would be another way to induce this pair of flags because I would end up with F1 up here. So really we have a third chance of choosing this guy to be 1, and then we have a half chance of actually choosing this other guy to be mated with him for F0. And the same thing happens here, so that's why we get this 1/3 in front of this dH1. When we find H1 as our subgraph, this is the contribution to this pair of subgraph counts. So this is H1's contribution. Let's do H2's contribution. So H2's contribution, we start off with this graph, H2. Well, what I claim is that we need either the label 1 to be down here, and then we get this guy F0, because then we miss this edge that goes between them with F1. There's another way to get this pair. Or instead, what we end up getting is we could, for example, have this guy labeled 1, and we could have F0 sitting down here. And that's exactly how you get this contribution from H2, the same way. So let me skip the other combinatorics, but let me just work out exactly what D of F1, F1 is. It's just elementary reasoning along these lines. So it turns out when you look at the different subgraphs, you get 1/3 dH2 plus dH3 when you look at the pair of flags F1, F1. But now we get to use our ideal. So when we work modulo this ideal of triangle-free graphs, we're going to remove this H3 term, and we get just 1/3 dH2 mod the ideal. So these are all of the elementary identities we're going to use. The first ones were just about subgraph counts and how they relate to the edge density of the graph. These more sophisticated ones were about pairs of flags which come from this probabilistic experiment. So now, in fact, we have all of the identities we need to prove Montel's theorem. Yep?
Sorry to be impatient or something. So far what you're showing, right?
Yeah.
The polynomials are just a bookkeeping device
Yeah.
for some counting argument.
Yeah.
Two ways of counting.
Yep.
Now somehow are you going to use sum of squares to say something else?
Better. That's a very good question. Ravi's right, I better. So let's do that.
Before you do that, so going back to this disjointly thing.
Yeah.
So in this example, you really are picking three distinct vertices.
Yep.
You don't so the F minus T vertices are disjoint.
That's right.
And
That's right.
That's always the case.
That's right. So we're going to see exactly, so if you chose these separately, this F minus T and F minus T in a way that they weren't necessarily disjoint, there'd be some chance that you would get a two-node graph because these things would collide. But the point is that that's actually a very low probability event. It's something that happens about 1/n fraction of the time when you're thinking about these things as being small constants. This is going to show up in the sum of squares proof that we're going to need an error term that accounts for the fact that we do sometimes have collisions.
But that's not in the D sub f.
It's not yet. Yep.
Wait, so when we're just using these two flags, F0 and F1, it doesn't. This sort of the fact that the unlabeled vertex is unlabeled doesn't actually matter at all, right? So we could have really just looked at the whole thing as we labeled all three vertices of the triangle. Is that
Sure.
right?
Yep.
Okay.
Yep.
But I assume that this flag machinery is a lot more general.
That's right. That's right. So everything I'll be talking about is a lot more general, but just to keep it simple, let's work with just this case. So let's figure out now how to actually prove Montel's theorem using these identities. So let me erase, let me erase this part and keep up the definition of flags and their probabilistic experiment. But let's use the identities we've developed. So, well, what are we going to do? We're going to start off with the half polynomial. And we want to subtract off this edge density polynomial, because we want to show that for any triangle-free graph, this is non-negative. That's our goal. So we're going to work modulo the ideal. And what I claim is, first of all, just using this identity about, this identity 2 right here, that 1 is equivalent to dh0 plus dh1 plus dh2, we can just scale everything by 2. And that gives us a way to plug in these subgraph counts over here, right? And we also have that relation in 1, which expresses d in terms of the other dhis. So what you end up getting when you do this out is just doing the elementary algebra. You get half dh0 plus 1/6 dh1 minus 1/6 dh2. This is all mod the ideal. Now I'm going to do something a little bit strange here, which is I'm going to add and subtract off two terms. So first I'm going to group expressions into a more convenient way. So I'm going to make this a minus 1/6 in front of the dh1. I still have the same minus 1/6 in front of the dh2, and I need to add back in my 1/3 dh1 in order to compensate for moving this around. So what I claim is that this guy right here is actually a sum of squares. This is something which is essentially non-negative up to this error correction term about when these two different flags collide. So what I claim is the following. Allow me to just write out an expression and then tell you what this thing means. So why is this actually a sum of squares? Is because there are some other polynomials that I can tell you what these represent in terms of our probabilistic experiment, which you can write out this way. Okay, so what do I mean by this is when we take a pair df theta and df prime theta, that's actually going to be the same thing as d of f prime plus minus some error term, where you're thinking about this error term as really being about 1/n. So what this means is that, so you could first do an experiment where you fix whatever the core is, and then you choose f and f prime uniformly at random from the rest of the graph into what fixes the rest of this flag. So all you're doing is you're actually doing this experiment where you choose the core theta, and that's roughly the same thing as actually forcing f and f prime to be, for example, disjoint, up to some lower order correction terms about whether or not these two flags collide. So the important thing is that this matrix in the middle right here is PSD. And what you do is when you have this identity that you could think about this experiment with f and f prime as coming from taking the core and then fixing the two separately so that they might or might not overlap, well, you could interpret it instead as a quadratic form, where you're actually looking at the expectation of this vector against this PSD matrix. So this is where SOS comes in, is just the fact that this is a PSD matrix, and this term right here actually is sum of squares, in the sense that you can think about the contribution of these terms as coming from a probabilistic experiment whose contribution is non-negative. So this is where the action was happening, but once you have this, what this means is that 1/2 minus this edge density polynomial plus this type of error term is actually non-negative modulo the ideal. Because this term right here is non-negative because we have this PSD matrix, which is governing how we construct this experiment. And the only other remaining term we have right here is 1/3 times dH1, which is definitely non-negative. So this is how you can use sum of squares to prove things like Montel's theorem. Is what this tells us now is that, just to translate what this means modulo the ideal, it means for any triangle-free graph, because that's what we substitute in when we talk about working modulo the ideal, we have that 1/2 minus the density of the graph when we evaluate it at the indicator function of g, plus this epsilon, this extra slack term, is actually non-negative. That's what this inequality modulo the ideal means. So this actually proves Montel's theorem, but it gives you a sense of how you can actually prove interesting relationships about subgraph density counts using things like sum of squares. The idea is trying to find some interesting identities, some things on the subgraph counts you're starting off with, and guessing the right flags that are going to show up in your sum of squares proof, and then figuring out how to get the desired inequality, which holds modulo the set of graphs you're considering. Yep?
So, the first part is sum of squares, but dH1 you haven't shown is not necessarily a sum of squares, right?
dH1? dH1 is non-negative?
Non-negative.
Yep.
For all real x's or only for the 0, 1?
Only when I evaluate it at the indicator functions of graphs.
So it won't be a sum of squares, for instance.
Nope. It's just something that's non-negative because it's a subgraph density count. So what I have is that I can express 1/2 minus the density of my graph modulo the ideal of these triangle-free graphs as a sum of squares coming from this experiment about pairs of flags plus something non-negative. And that's the proof of Montel's theorem.
So is it easy to show that this expression out here, this expectation, is that?
Yeah, so what you would really do is you would just figure out what this probabilistic experiment is and handle these types of collisions. And then just the fact that it is a PSD matrix, which you're taking a quadratic form of some vector on it. So
some calculation that
exactly. Yep, exactly. Because this is just some average of non-negative terms. Yep.
Easy to check, but is it easy to find this? Can you see that it's a quadratic form how do you get from that line?
Right, so for example, this is the part that you would check right here, is that when you actually do this experiment, where you end up choosing the core theta randomly, that you can look at the expectation of this pair of these polynomials, which are two independent experiments. And the point is that you actually get a relationship to the pair of experiments f and f prime, where you choose them disjointly. For example, up to some extra slack term.
Maybe I'm asking, where do you use those inequalities that you
Yep.
You want to check the expectation.
Yeah, exactly. So for example, when you actually want to check this expectation, so first of all, I used these, so I used only 1 and 2, the identities, to prove this part right here, because I just expressed 1/2 and the edge density in terms of the subgraph counts. But where I actually used the inequality, the identities about flags, was in going from here to here. So this is the thing that you check, is that if you have this quadratic form, you can figure out all of the different terms in this quadratic form. They all look like things like this for different pairs f and f prime. And then I can use this identity about how that relates to the different pair of flag experiments that we talked about. And then I use all of those identities to figure out that this is the same thing as this. So this is some algebraic calculation.
So
kind of related to that question. So how can someone come up with pairs of flags and a way of decomposing it into this X transpose QX by just looking at the expression you have for the half minus t?
That's, how do you want to answer?
Yeah, I mean, let me just contrast this with, or compare it exactly what they did in the polynomial case, right? And essentially, when you look at something more the ideal, then, if you start essentially picking polynomials and monomials up to a certain degree.
Yeah.
So here, I mean, in practice, you would do exactly the same thing. You pick flags up to a certain size. You pick all flags up to a certain size. And how do you find that matrix in there? You solve the semi-definite problem.
So this is the part of proof system that's automatizable up to some degree or up to some number of extra nodes in the flag.
I see. So the STP that you solve is basically having affine constraint coming from the
That's right.
coefficients.
Exactly. Exactly.
Yes, and then
Exactly.
you expand the expression.
Gotcha.
Exactly. Any other questions about this? Yeah.
Is there a, if you were to look at that expression sort of and stare at it in an elementary way, would you be able to prove without sum of squares that that's non-negative?
It really amounts to the PSD-ness of this guy.
But so why are in some sense, the flags so important? Why do we have to start labeling? Or why wouldn't we be able to get it without labeled graphs? I don't know.
Because we need this type of, in order to express it as a quadratic form in this way, we do need to talk about, how looking at different experiments in isolation, looking at just the experiment for f and just the experiment for f prime, relates to the pair, the composite experiment for f and f prime. And that really requires talking about the common core that's being fixed. That's what's happening within this theta. That's what's enabling this sort of sum of squares proof, is the fact that you're allowing some part of it to be labeled so that you can figure out how these two things interact with each other.
Question.
Yep.
So, and the size is 2 by 2 because you are looking at triangles, or?
Which size? This? Yeah. Yeah. It's because we're looking at pairs of flags, which there's one node in the core. And then there's one node outside the core in both of the two flags, because we look at F0 and F1. So that's why we're always choosing, when we try and relate that experiment about pairs of flags to our original subgraph counts, which is what we did in these different identities, that enabled us to go from this to this style of expression. That's why we needed to talk about triangle counts here, was because of the pair of flags we had in mind.
Right. But if you want to explain the right side of the picture, would we need richer flags, or?
The right side?
The graph that you plotted, which is
Uh-huh.
those curvy things.
Yeah, then you need some pretty fancy things.
And the matrices would be larger?
Yeah, yeah, much larger. It's not quite this simple. Yep.
So in this technology, do we ever need more than one label, or?
Yes, definitely, definitely. A lot of yeah. Yep.
Does your SOS problem also have the constraint that x is just 0 or 1? Do you have an S procedure in there for restricting x to the?
So a lot of times you can talk about SOS using a constraint, something like Booleanity. So that I'm going to come to actually when I transition to the next topic, which is something called pseudo-expectations, which is a dual and complementary view to the view that Pablo introduced in the first two parts of this tutorial. That'll be the mechanism by which we get some of our algorithms and the connections to things like quantum. Yep.
So in the first board, after the second line, how come you didn't use what you wrote in the third board with these T, F0, F0, and so on?
Here?
To change basis from the DH something.
So what you do is you go from the second to the third line using this set of identities.
Change to this and then introduce the epsilon arrow.
Exactly. Perfect. All right. Yep.
What do we know about the expressiveness of this proof system?
So, something that's, this is a huge topic outside, but, something interesting you can ask all sorts of relationships about pairs and higher order k-tuples of subgraph counts. And what's kind of remarkable is a result of Hamed Hatami that shows that actually figuring out which types of inequalities about subgraph counts hold for all graphs and which ones don't is actually an undecidable problem. So eventually, you encounter some pretty scary beasts in this type of thing. Now, these types of, this isn't Razborov's original version, but this is a version of it, a view from SOS, which you can use to fully resolve this picture about triangle counts versus edge densities. But when you go out to the most general versions of the problem, you will encounter undecidable problems in this landscape. All right, so we're actually somewhat close to the end of the first hour. This was supposed to take a little bit less time, but that's okay. I'm going to cut some stuff at the end. So maybe now is a reasonable time to take a break. And what we'll do is in part 4 of this tutorial, I'm going to explain how to round sum of squares algorithms using a probabilistic viewpoint, and how that actually relates to some very fundamental questions in quantum information theory. So one of the things I really wanted to get across in this tutorial is that SOS connects to all of these other areas in math and physics. And sometimes you hear about these connections, but actually seeing what they mean in an elementary language is a bit non-trivial. So once we get to quantum, we're going to see how polynomial optimization and results about how well SOS performs relates to things like quantum Di-Finetti theorems that I'm going to explain, I promise, without any bras and kets. All right, so let's end there for the time being.
Are there any final questions for Ankur? Since we do have a couple of minutes.
What was the result of Riemann?
So it's a way to translate flag algebra proofs into the SOS language, which the crucial thing is how to make sure that the semi-definite programs that you get out are constant size. So it heavily uses some results of Pablo and Gaterman, which use representation theory to say that when you have symmetries in the optimization problem you're solving, that you can work with much more restricted sets. So the sort of virtue of Razborov's flag algebras approach is that they're always constant size types of things. Now they can be prohibitive to actually solve these things up to some degree, but how to get all of the flag algebra machinery working within SOS with constant size semi-definite programs.
Otherwise, you just do some other brute force algorithm, or what does it buy computation?
As in, you want, if you're looking for constant size proofs, like up to degree d, you definitely don't want your semi-definite program to run in n to the d time, where n is the number of vertices. So you want it to run in some constant amount of time, that for constant d.
Which is independent of n.
Which is n here? N is the number of nodes in the graph.
But in these identities, there is no n, right? In some sense.
Yeah, that's right. But if you want to prove it, for example, there are certainly n's and the number of variables in these polynomials.
Nice.
Yeah.
Is there also an issue with the error bounds that are coming into play?
Yeah. So for example, this is actually a weaker form of Montel's theorem already, because Montel's theorem was extremely sharp. Like it first of all didn't have, it said, floor of n squared over 4. Now first of all, this is an asymptotic version that, we get that 1 over 4 in there. But because of these error terms, see the inequality we're proving about subgraph densities already has the slack up to something that goes to 0 with n. So that's a property of these types of proofs, that when you translate between df f prime and this expectation over theta of df theta df prime theta, you are going to encounter these types of overlap, these error terms that account for overlaps and collisions between the two different flags. So that's one aspect, is that actually what we did was we gave a very high-tech proof for a slightly weaker result than Montel's theorem, which, as I promised you, we do in undergrad discrete math on our tests. Yep.
So I'm not sure if this is what Chandra was trying to ask. I guess people were using the flag algebra technology to verify prove some work by Raymond and Thomas. Does it explain mathematically what's happening, or computationally does it offer somehow a better way to do it?
Can you repeat that a little bit louder?
Yeah.
The flag. It might be better if you heard me, if you repeat it, so everybody.
Well, I mean, so that work of Raymond et al., what it does is it connects.
I need to repeat the question.
Okay. Actually, could you repeat the question?
You can answer anyway, but
I think I got it, but I don't want to butcher the question.
Was, flag algebra machinery of Rasborough was there. It's been there for several years, and people verified graphs and hypergraphs. Some conjectures using that. And then the recent work by Raymond St. Thomas connects it to
SOS.
squares.
Yep.
So I'm asking, I think Chandra also alluded to, what's the advantage? Is it mathematical, computational, both?
I'm going to defer to Pablo.
So let me explain that way. I mean, somehow the...
Could you repeat the question?
You see what I'm dealing with? Should we just go?
So I think the main point, I think the really great point that happens in that paper is that essentially say that you can recover that the flag algebra is nothing but when you take sum of squares and you do symmetry reduction and you let n go to infinity. And then flags are nothing but, in a sense, the equivalence classes that you get when you quotient with the action of the symmetry group in the asymptotic limit. And only finitely many irreducible representations are going to appear in the symmetry, in the decomposition of these polynomials, and those irreducible representations are exactly the flags. So
maybe it removes the mystery from the flag algebra.
Certainly, in retrospect, one could have just done, the flag stuff without being Rasborough. But and the point, what I think it's perhaps, if you ever try to read Rasborough's papers, that paper, without somehow understanding the big picture or whatever, it was really a mystery. Not just to, I think many people had, this sense of, okay, wonderful theory, you can compute lots of things. How did he ever think about, doing these kind of things? And somehow really, I think what that paper is a very nice link from, somehow a very concrete question about, okay, I really just want to show the negativity of, a polynomial. The problem is that the number of variables goes to infinity, so it would seem as if you would have to solve, semi-definite problems of size that grows with n. But, essentially, when you look at this, asymptotic version, and, you ignore this, you prove that you can ignore this order 1 over n terms, then everything becomes, collapses to these other semi-definite problems in this by flags.
Do we know then the reach of what flag algebras can and cannot prove? Is there some well-delineated threshold, or is that?
There are still, pretty elementary open questions in the hypergraph versions of these things where we don't even understand the asymptotics for the counts. So it's to say that there's still plenty of interesting things where we don't really understand what all these techniques could be used to prove.
But in the sense of how the positive Stalinsatz will tell you that any reasonable inequality, if you go up to high enough degree, you can prove it.
But there are things which are undecidable.
So the part that we cannot understand is what can be shown with a constant number of flags. So if you were to let the number of flags go to infinity with n,
then you get positive.
Okay. And that's always the game in these types of things, is we don't understand what the power is for d being a small constant, d being logarithmic, that kind of thing. So this is a great time to segue until quantum, where the d really represents when you create composite states, how symmetric they are and how close they become to nicer, more classical objects that we can reason about. There, the name of the game is always having some quantitative bounds in terms of d, but the same way here, some of the mystery is what can you get out with constant size, proofs. All right, so thanks again.